Hello students. Today topic is Gauss theorem. Gauss law is one of the fundamental law of physics. It relates the electric field to the charge distribution which has produced this field. As you all are familiar with the electric flux is equal to surface integral of E dot ds, which is equal to Q upon epsilon naught. So in this topic we will find the relation between electric field and charge. It relates the electric field to the charge distribution which has produced this field. So according to this theorem, the surface integral of electric field produced by any source over any closed surface S enclosing a volume V in vacuum, that is total electric flux over the closed surface S in vacuum, is 1 upon epsilon naught times the total charge Q contained inside S. Total electric flux, that is surface integral of E dot ds. If there is a closed surface and there is a charge plus Q present at the center, then due to this charge there will be electric field E. If we choose a small area element at point P whose surface area is ds, and r is the position vector of point P, r cap is the unit vector along the direction of electric field or along the position vector r, n cap is the unit vector of area vector. As you know, area vector is always normal to the surface. So according to Gauss theorem, total electric flux, that is surface integral of E dot ds over a closed surface S. This is the closed surface, its volume is V in vacuum, is equal to 1 upon epsilon naught times total charge Q present inside the surface. This imaginary spherical surface chosen is called Gaussian surface. Gaussian surface is that surface at every point of which the electric field intensity has the same value. It is an imaginary surface chosen. Now we will prove that total electric flux is equal to 1 upon epsilon naught times charge. The Gauss theorem is applicable for spherical symmetric surfaces only. If we find the electric field at point P, the electric field due to charge Q is equal to Q upon 4 pi epsilon naught r square. R cap is the unit vector directed from O to P. Electric flux over the area element, this area is small ds, so electric flux through it is d phi. This is equal to E dot ds, E equal to Q upon 4 pi epsilon naught r square into r cap dot n cap ds. Electric field, the magnitude of electric field is q upon 4 pi epsilon naught r square, and r cap is the unit vector along position vector r or along electric field E. ds is written as n cap ds. ds is the magnitude, n cap is the unit vector normal to area directed outward. Now E dot ds equal to q upon 4 pi epsilon naught r square ds r cap dot n cap. The dot product of r cap dot n cap, r cap dot n cap, both are along same direction. So magnitude of r cap dot n cap cos of angle between them, and angle is 0. Magnitude of unit vector is 1. Magnitude of n cap is also 1. Both are unit vectors. Cos 0 is 1. So this will be equal to 1. So r cap dot n cap equal to 1. Now E dot ds is equal to q upon 4 pi epsilon naught r square ds r cap dot n cap becomes equal to 1. Now this is the electric flux through the small area element ds. We have to find the total electric flux over the closed surface S. So we will integrate it. So integrating both sides, we get phi equal to surface integral of E dot ds equal to q upon 4 pi r square epsilon naught r square surface integral of ds. Surface integral of ds means total surface area of the surface. So total surface area will be equal to 4 pi r square. So this will becomes equal to q upon epsilon naught. 4 pi r square, 4 pi r square cancel out. So phi E, that is total electric flux, is equal to q upon epsilon naught. Now if there are number of charges q1, q2, q3, qn lying inside the surface, then each will contribute to the electric flux. Total electric flux will be equal to sum of electric flux due to individual charges, phi E1, phi E2, phi E3, so on, phi En. Phi E1 is the electric flux due to charge Q1, so this is written as Q1 upon epsilon naught plus Q2 upon epsilon naught, Q3 upon epsilon naught, so on, Qn upon epsilon naught. 1 upon epsilon naught is taken common, so inside the bracket Q1, Q2 plus Q3, so on, Qn. So this is equal to total charge Q. So if the medium surrounding the charge has dielectric constant K, means medium is other than air, then epsilon naught, in place of epsilon naught we write K times epsilon naught. Permittivity of the medium, K is dielectric constant, epsilon is the permittivity of the medium. So formula becomes phi E equal to Q upon epsilon. Now there are certain points that should be kept in mind. First is charge inside S may be a point charge or even continuous charge distribution. So inside the Gauss surface, the charge can be a point charge or a continuous charge distribution. Gaussian surface is an imaginary geometrical closed surface at every point of which electric intensity is same. So why we have chosen Gaussian surface to be spherical? Because to make our calculation easy. To solve this integration E dot ds, this integration can be solved only when electric field is constant, and for a spherical Gaussian surface electric field has the same value, so it is constant, so it can be easily solved. So since E is constant, it is taken out of integration, and we can find the integration of ds. If theta is 0, it will becomes 1, so it can be easily solved. That's why we choose a symmetric Gaussian surface. It can be a sphere, it can be a cylinder. Next is, it may lie in empty space or in a solid body. Gauss theorem holds good for any closed surface, regardless of its shape and size. The surface should be closed. Gaussian surface does not pass through any discrete charge. An electric field is not well defined. So when we choose a Gaussian surface, it should not pass through any charge. Either charge should be inside the surface or should be outside the surface. Now when we choose surface in which there are some charges inside and some outside, the electric field E is due to all the charges, but Q represent only the charge present inside the surface. When we apply Gauss theorem, the Q is the charge which is present inside the surface, not outside the surface. Gauss theorem is used most commonly for symmetric charge configuration.